Okay, so um, interval level variables, right, are those that are measured, in numbers. They're in a survey. They typically open-ended questions where the answer choice is a number, right? That can range from any value to any value. So when analyzing categorical variables, we use frequency distributions, right? Now, in most cases, constructing these frequency distribution tables for these variables that are measured at the interval level would not be feasible, right? For example, creating a table of all the values of the variable age, for example, all right? If we have thousands of observations, we can have, I don't know, hundreds of values, right? Even that we can have potentially. So creating a table to analyze a variable like this is not feasible, right? But we don't need to, right? So the good thing about interval level variables is that we can summarize how they're distributed with just a few numbers, right? We can do that with measures of central tendency and measures of dispersion, which is the focus of this lecture. We don't really need a table or a chart to show us the distribution. But there are some charts that can help, right? One of those charts is a histogram that it follows the same logic of a bar chart, right? It actually makes a variable that is interval level into a sort of categorical variable that puts values in certain categories and then plots those categories, right? But sometimes it's hard to do that, and we don't need that all the time, right? This is an example of a histogram, right, of respondents' age in the general social survey, right? So I asked my computer, and this is a special software, Google Sheets doesn't have that, to create a histogram. And it said, all right, it created all these categories for me and it plotted them just like a bar chart. And it said, hey, from 18 to like say 25 or something like that. This is the width. 12% of the population are in that category. And from 28 to the next category to 33, so 17%, and so forth. So here we can see, all right, well, we have about 11% in this age bracket, and about 4% are older than 80. It kind of gives you a picture of how the variable is distributed, right? However, you can get some information of how it is distributed with just a couple of numbers, right? And these numbers are some of them are measures of central tendency, right? And one of them you know very well, right? That one is the average or the arithmetic mean, right? When you say the mean of a distribution or the average number of a distribution, it's this expression, right? Is the sum of all those numbers, of all those values for all the observations, divided by the number of observations, right? That's how you get an average, right? And this is the the notation for that. So the average of the variable x, right? And the average, we usually put a bar over it, right? X bar is usually the mean of x in statistics and notation. So equals to the sum of all the values of x, right? From the first one, when I equals 1, to the last one, when I equals n, right? N divided by n. That's and n is the number of observations, right? So, for example, if the variable x has 11 observations, and these are them, right? The first value, the first observation for that variable is 9, the second is 8, and so forth. So for the mean, we just add all those values, right? 9 plus 8 plus 2 plus 2 plus 4, add them all. and divide them by the number of observations, which is 11, right? 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. And the mean is 3.82, right? So the mean gives us an idea of the distribution, right, in one number, right? It's 3.82. If we add all the values and divide it by the total number of observations, we get 3.82. That's the mean. We all understand that. Another measure of centrality is the mode. We can use that to describe a distribution too, right? And the mode is the value that has the highest percentage of occurrence in the set. It is the value that is most common, okay, in a distribution. The mode is useful with, you know, when you have very few values, right? And you know, it's pretty useful, but not so much when you have a lot of values. But anyway, some people use it, and we should use it, and we should just talk about it for a little bit. So in our example, right, the mode is 2, right, because it is the value that is most common in out of all those 11 observations, right? There's 4 2s, right? And 2 is, you know, the most common of all those numbers. So the mode is just 2, right? There's no formula for this. It's just seeing which one is the most common, and that is, even if it's just repeated twice, right? But that's, you know, that would be the mode, the one that is, you know, repeated the most. Sometimes you have distributions that have 2 modes, right, where 2 numbers are repeated at the same time. Another one that is super useful is the median, right? And the median reflects the middle value in a series of ordered observations in a set, right? It's the number that divides an ordered distribution into 2 identical halves. Right? So to calculate the median, we would order all the values, right, in the distribution, and we will look for the one that is in the middle, and that value is the median, right? And so in order to look for which value is the median, we can use this little formula, right? We can have, and it's n, the number of all of the observations, plus 1 divided by 2, and that tells you the number of observation that is giving you the median. Let's look at an example. Remember, this was our distribution, but now we have ordered it, right, from the lowest value to the highest value. So there were 11, right? 11 observations here. So the median is the middle value there. So if we want to find it quickly, we can use this. We just put 11 in that little formula. So 11 plus 1 is 12, right? Divided by, that, yeah, 11 plus 1 is 12, divided by 2, that's 6, not 5, right? So 1, 2, 3, 4, 5, 6, that is our median, right? So disregard this, I'm going to change it. It should be 6. But the value is 2. Now, notice that the value is 2, right? We didn't calculate this in any way. We just order it and we look for the value that is in the middle. If we take that value, we have an equal number of values to the right of it and then to the left of it, right? It's the median is the value that divides the distribution in exactly 2 identical halves. If we had an even number of observations, then the median will fall in between 2. Right? If that happens, we just take the average of those 2, and that's the median. In this case, we would, the average of those is 2. So the median would still be 2 if we had 12 observations. All right. So how do we interpret the median here? Well, if you look at the red text, that's how I want you to interpret any median, right? I want you to say that half of the observations are at or below the median, and half of the observations are at or above the median, right? So if we were told that, for example, the median income for households in Monterey County is $60,000, then how do we interpret that number? We would say half of the households make $60,000 or less, right? And the other half of the households make 60,000 or more, right? That's how we would interpret a median. And the median is very useful because it tells us, regardless of the distribution, how it looks, it tells us, hey, the number in the middle is that, right? So it gives us a mental picture of what that distribution looked like. Now, the median is very useful when you also have a mean for that distribution. Okay. Now let's see what's happening in this. This is the age, right? And I calculated for this distribution that I already plotted using a histogram, right? I got the mean, right? It's there. It's 49 years old. The median is 48, right? And the median is the value in the middle of the distribution. And the mode is 34, right? 34 is the value that is repeated the most. Now, one way to think about the mean, right, or the average, is that is the value that sort of balances the whole distribution, right? If this distribution would look like, it had a tail, like a long tail there, the mean would be pulled there because it has to balance. If you had to put, a distribution in a like in a balance, right? Let's say, let's use a pen here, and you want this pen to just stand there, right? We have to pick the point where it would balance perfectly. That's what the mean does. If it's very heavy on this side, then we would have to put it right here. But the median is always in the center. The median is always in the center, but the mean sort of is the one that balances, right? And that's a very important point, because when you have a mean and a median for any distribution, you can sort of make sense of how the distribution is distributed. I mean, it's skewed, right? Or what it looks like. When the mean and the median are the same, right? That means that the distribution is symmetrical. Like it has exactly the same sort of values to the left that it has to the right, right? It's symmetrical. When the mean is higher than the median, that means that there are some extreme values that are pulling the mean to a higher end, right? That's when the mean is higher than the median. And when the mean is lower than the median, it means that there are some extreme low values there, right? And that's one of the problems with the mean, that very high values can skew the whole distribution, or it can pull it in some direction, but that doesn't happen with the median, right? So, and this skewing effect is sometimes called the Bill Gates effect. Bill Gates is the guy who founded Microsoft, right? Windows, Microsoft Excel, all of those things. So he's a billionaire. At one point, he was the most or the richest man in the world. So, and so imagine that we have this Zoom meeting with 6 participants, and we say, hey, let's see what's the average amount of cash we have with us. So I asked that, and all of us, we get our wallets, and we see how much cash we have. Hey, I have 5. You have 10, you have 2, you have 3, you have, well, 100. Wow, that's great. Let's say and we calculate the average with that, right? Perfect. And then Bill Gates comes into the Zoom meeting, and he says, "Oh well, I happen to have $10,000 in my wallet." Right? When we add him to our little group distribution, the average income for the group would go way up, right? Because we're adding 10,000 to our 1, 5, even 120, and then we add the 10,000, and the mean is going to be somewhere around, $2,000-3,000, and that's for super a lot higher than we had before Bill Gates came in, right? So that's sort of the problem with the median. When you have an extreme high value, the mean is pulled in that direction. But the median, if we calculated the median before Bill Gates walked into our or logged into our Zoom meeting, the median, let's say, was the middle value in our distribution. In the example I gave was, I think, $10, right? If Bill Gates comes in, he just one more value. We add it there, and the median is still, probably 10 or very close to 10, between 10 and 20. So if you have a distribution where the average is, let's say, $20, but the median, if you have a distribution where the median is $20 and the average is 2,000, then you know that there is one or a few observations that are way, way out there, right? So that's how knowing the median and the mean is very important, right? In the census, for example, or in many economic statistics, they prefer the median because there's always some extreme values out there, right? Like house price or home prices in Monterey County. We don't talk about the average house price because there's a few mansions that are way out there in the 20 million or so, and they pull that average very high. So we prefer to use the median and say the median house price in Monterey County is, I don't know what it is exactly, but it's that median is one that half of them are at that value or above, or half are at that value or below, right? Without worrying about some extremes pulling it in either direction. So that's the mean, the median, and the mode. Other measures of dispersion this time that let us know how a distribution is distributed or looks like are measures of dispersion, right? And the measures of dispersion let us know how far the observations are falling from a mean, right? And the standard deviation is one of those measures of dispersion that we'll talk about. So in this case, right, we have a distribution here with a standard deviation of 5, right? In both of them, the mean is the same. And you see in that one, most of the observations are falling pretty close to that mean of 15, right? Most of them. And on this one, observations are falling a little further away from 15, right? See, 35 is here, a lot of more are falling above 40 and so, or below -10. And this one has a bigger standard deviation, right? So these measures of dispersion tell us how far the numbers are falling in the distribution from the mean, right? The standard deviation comes from the variance. Don't worry about this formula. You're not going to calculate this manually because we have Excel for that. But that's what it does, right? I want to show you what the variance means, right? This is the variance of x, right? Sometimes expressed as s squared x. It's just the sum of every value, right? This is every value in the distribution. So you get the mean and subtract it from, subtract every value from the mean. You square that difference and you add it all together. And you divide it by the number of observations minus 1, right? So here, if we had a distribution, this is the number, this is the one that we've been talking about all this lecture, and this is the mean. Remember, we calculated that. We get, so from the mean, we subtract the value, right? So for this observation, we did that, and we square it, right? And we do the same. We subtract here and we square that. And when we add all together and divide by n minus 1, in this case, by 10, right? And it's 11. And that is the variance, right? And it gives us a measure of how far the observations are falling from the mean, right? But the variance is the squared, right? And one reason why we square it, right, is that negative numbers squared are positive, right? So we want to square so that we have that so negative numbers are adding, so it's just deviations, right? And the standard, because it's squared, it's not very useful, and it's usually huge numbers. So the standard deviation is usually just the square root of the variance, right? Not usually, always. The standard deviation is the square root of the variance. And the standard deviation is, again, a measure of how far observations fall from the mean, okay? And it's very useful when you have a standardized observations. You can talk about their values not in the units of the variable, but in terms of how far they fall from the mean, right? When you standardized observations and you subtract, the distribution mean from the value, and then you divide it by the standard deviation for that distribution. And then you do that for every value, and then you have your value expressed on how far it falls from the mean. For example, here, this is standardized. So this value of 9, we know that the mean is 3.82, right? So this one is pretty far away from the mean, right? And it is 1.83 standard deviations away from the mean. This one is 1.48 standard deviations away from the mean. This one is a little below the mean, right? It's 0.65 deviations below the mean, right? So we're not expressing each observation in terms of its units, but in terms of how far away from the mean it falls. And this is going to be very useful later on when we do hypothesis tests and we do other types of distributions, right? One of the most useful things that we have with the normal distribution, or findings that we have from the normal distribution, is that most of the observations fall within 1 standard deviation from the mean. 95% of all observations fall approximately within 2 standard deviations from the mean, and 99% of observations fall approximately within 3 standard deviations from the mean. This is a very cool trick to evaluate, where any observation falls in a distribution. All right. So remember, this is the 68, 95, 99 rule of normal distributions, and it says that 68% of all the observations we're going to see in a normal distribution are within 1 standard deviation away from the mean. 95% are within 2 standard deviations away from the mean, and 99 fall within 3 standard deviations away from the mean. Okay,